There is a thing which I've known since I was young, since those early days at Harvard when I was still uncertain whether my life would belong to chemistry or to physics, and when the world seemed full of problems that were merely difficult rather than impossible. A thing which seems, when one first hears it, too gentle to be consequential. Light can push, not metaphorically, not in the poetic sense in which we speak of a sunrise pushing back the darkness, or a beam of light pushing through a window to illuminate a room, though these images have their own truth, and I would not dismiss them. I mean physically, mechanically, measurably. A beam of light falling upon a surface exerts a force, a pressure, a push. And this push, this impossibly delicate, almost imperceptible nudge, is sufficient, given enough light and enough patience, to move objects through the void of space, to propel a craft across the solar system, to send a vessel to the stars. The same physics that illuminates a page can move a world. And this, I think, deserves some careful thought. I should like to examine what it means, not merely what the equations say, though the equations are beautiful and precise, and I shall not neglect them, but what it means that the gentlest thing we know, the thing we associate with vision and warmth and clarity, with the paintings that hung on the walls at 155 Riverside Drive when I was a boy, with the desert light of New Mexico that I loved more than almost anything in this life, that this gentle thing carries within it the capacity to exert force, to do work, to push matter from one place to another. Because there is in this fact a quality that I find both hopeful and unsettling, and the two are not, as one might wish, easily separated. Let me be precise about the physics. The idea that light exerts pressure is not new. Johannes Kepler proposed it in 1619 in his treatise on comets, observing that cometary tails always point away from the sun, as if blown by some solar wind. He was right about the observation, though the mechanism he imagined was not entirely correct, and it would be nearly 3 centuries before the physics was properly understood. It was James Clerk Maxwell, working in the 1860s, building the theoretical framework that unified electricity, magnetism, and optics into a single magnificent structure, who showed that electromagnetic radiation carries momentum. This is a consequence of his equations, and it is one of the most remarkable consequences of any set of equations in the history of physics. An electromagnetic wave, light, radio waves, X-rays, all of them manifestations of the same fundamental phenomenon, carries energy, and it also carries momentum. And where there is momentum transfer, there is force. And where there is force distributed over an area, there is pressure. The magnitude of this pressure is given by a simple relation. For light that is fully absorbed by a surface, the radiation pressure equals the intensity of the light, the power per unit area, divided by the speed of light. For light that is perfectly reflected, the pressure is doubled, because the momentum change is twice as great. The photon reverses direction, and Newton's third law, as always, is meticulous in its bookkeeping. At the Earth's distance from the sun, 1 astronomical unit, approximately 150 million kilometers, the solar intensity is roughly 1,361 watts per square meter. This is what we call the solar constant, though it is not, in fact, perfectly constant. It varies by about 0.1% over the 11-year solar cycle, a detail that is important for climate science, but not for our present purpose. Dividing this intensity by the speed of light, 3 times 10 to the 8th meters per second, one obtains a radiation pressure of approximately 4.5 micropascals, 4.5 millionths of a pascal. For reference, atmospheric pressure at sea level is approximately 101,325 pascals. The radiation pressure of sunlight is roughly 20 billion times smaller. One might at this point be forgiven for concluding that the whole business is trivial, an academic curiosity, a footnote in the long history of optics, a force so small that it could not possibly matter for anything practical. And indeed, for objects of ordinary size and ordinary mass on the surface of the Earth, surrounded by air and subject to gravity and friction and all the other forces that dominate our daily experience, radiation pressure is negligible. You do not feel the sunlight pushing you when you step outside. The book on your desk does not slide across the table under the pressure of the reading lamp. These are not failures of the theory. They are consequences of scale. But scale, as I learned over many years and at considerable cost, is not destiny. What is negligible at one scale may be dominant at another. And in the vacuum of space, where there is no air resistance, no friction, no weight in the gravitational sense that we experience on the surface of a planet, in space, the patient, relentless, infinitesimal pressure of sunlight becomes something else entirely. It becomes a force that can move worlds. Or, more precisely, it becomes a force that can move spacecraft, if the spacecraft are designed to receive it, if they are given sails, as ships on the ocean are given sails, to catch not the wind, but the light. The idea of a solar sail is usually attributed to the Russian pioneer of astronautics, Konstantin Tsiolkovsky, who discussed it as early as 1921, and to Friedrich Zander, also Russian, who developed the concept further in the late 1920s. But the physical principle was established by Maxwell's theory decades before anyone thought to apply it to navigation. And the experimental confirmation came from the painstaking work of Pyotr Lebedev in Moscow in 1900, and Ernest Nichols and Gordon Hull at Dartmouth in 1901. Experiments so delicate, so sensitive to error, so vulnerable to the confounding effects of radiometric forces and thermal convection, that they represent a triumph of experimental physics that I think is insufficiently celebrated. Lebedev, in particular, worked with apparatus of extraordinary refinement. Thin metallic vanes suspended in a near vacuum, illuminated by arc lamps, measured by the tiny deflection of a torsion balance. He confirmed that the pressure of light on a reflecting surface was approximately twice that on an absorbing surface, exactly as Maxwell's theory predicted. The light pushed. The measurement agreed with the equations, and a door opened. Not immediately, not dramatically, but with the quiet inevitability that characterizes the deepest moments in physics. And here one must consider what it means to sail on light. A solar sail is, in its simplest conception, an extremely thin, extremely large, highly reflective membrane, typically aluminum deposited on a polymer substrate with a total thickness of perhaps 4 to 7 micrometers, thinner than a human red blood cell, deployed in space and oriented to catch the sunlight. The force per unit area is small. Those 4.5 micropascals at Earth's distance from the sun doubled to roughly 9 micropascals for a perfectly reflective surface. But the force is continuous. It does not require fuel. It does not require combustion. It does not require the expulsion of mass, which is the principle upon which all conventional rocketry is based. Newton's third law applied to hot gas, the Tsiolkovsky rocket equation that relates final velocity to exhaust velocity and mass ratio, the tyranny of the exponential function that makes every kilogram of payload require many kilograms of propellant. A solar sail carries no propellant. Its fuel is the sun. And the sun, in its profligate generosity, radiates approximately 3.8 times 10 to the 26th watts of power in all directions, a luminosity that has been essentially constant for billions of years and will remain so for billions more. It is, for the purposes of a solar sail, an inexhaustible engine. The acceleration of a solar sail depends on the ratio of the sail's area to its total mass, what engineers call the characteristic acceleration, typically expressed in millimeters per second squared. For a sail with an area-to-mass ratio of 10 square meters per kilogram, which is ambitious but not beyond current technology, the acceleration at 1 astronomical unit is approximately 0.06 millimeters per second squared. This is, I freely acknowledge, not impressive by the standards of chemical rocketry, where accelerations are measured in meters per second squared, or even in multiples of g. But chemical rockets burn for minutes. A solar sail accelerates for years, and this makes all the difference. An acceleration of 0.06 millimeters per second squared, sustained continuously for 1 year, produces a velocity change of approximately 1.9 kilometers per second. Over 5 years, it is nearly 10 kilometers per second. Over decades, the velocities become remarkable. Tens, eventually hundreds of kilometers per second, approaching and potentially exceeding the velocities achievable by any propulsive technology currently in existence. The Japanese Space Agency, JAXA, launched a spacecraft called Icaros in 2010, interplanetary kitecraft accelerated by radiation of the sun, an acronym that I suspect was reverse engineered from a desire to invoke the Greek myth, which is, given the subject matter, understandable if not entirely reassuring, since Icarus, one recalls, came to grief when he flew too close to the sun. Icaros deployed a sail of 14 meters diagonal, made of polyimide film 7.5 micrometers thick, and it demonstrated, for the first time in deep space, that solar radiation pressure could indeed accelerate a spacecraft. The acceleration was measured, the physics was confirmed. Maxwell's equations, written in a study in London in the 1860s, were vindicated in the vacuum between Earth and Venus a century and a half later. It is a profound and necessary truth that the deep things in science are not found because they are useful. They are found because it was possible to find them. The usefulness comes later, often much later, and in forms that the discoverer could not have imagined. But there is another dimension to this, a dimension that is, I confess, closer to my own preoccupations, my own particular history with the relationship between physics and its applications. The same radiation pressure that can propel a solar sail can, in a different configuration, with a different source of light, become something considerably less benign. There have been proposals, serious proposals by serious people, for directed energy propulsion systems that would use high-powered lasers, not sunlight, to push a sail to velocities approaching a significant fraction of the speed of light. The Breakthrough Starshot Initiative, proposed in 2016 by Yuri Milner, with the endorsement of, among others, the late Stephen Hawking, envisions an array of ground-based lasers with a combined power of approximately 100 gigawatts, 100 billion watts, roughly the total electrical generating capacity of a small nation, focused on a sail perhaps 4 meters in diameter, accelerating a gram-scale payload to approximately 20% of the speed of light. At that velocity, such a craft could reach the nearest star system, Alpha Centauri, in roughly 20 years. The physics is sound. The engineering is at present far beyond our capabilities. But the principle is clear, and the principle is radiation pressure, the same gentle push that deflects a comet's tail, scaled up by a factor of billions through the application of coherent, focused, high-powered electromagnetic radiation. And it is here that one finds oneself on familiar and uncomfortable ground, because a laser powerful enough to push a spacecraft to a fraction of the speed of light is also a laser powerful enough to do other things, things that I do not need to enumerate, because the imagination, once it has been pointed in this direction, supplies them readily enough. The history of physics, my history, the history I have lived and cannot escape, is in part a history of discovering that the same principles which illuminate can also destroy, that the same force which propels can also annihilate, and that the line between the two is not a line of physics, but a line of intention, of choice, of the moral seriousness with which we approach the powers that understanding grants us. I have asked myself many times whether it is possible to separate the beautiful from the dangerous in physics, to take the solar sail and leave the directed energy weapon, to take the reactor and leave the bomb, to take the light and leave the fire. And I have concluded, reluctantly but honestly, that it is not. Not because the physics is different. The physics is exactly the same in both cases, but because the understanding is indivisible. You cannot understand radiation pressure well enough to build a solar sail without also understanding it well enough to build a laser weapon. You cannot understand nuclear fission well enough to build a reactor without also understanding it well enough to build a bomb. The knowledge is one, the applications are many, and the choice between them falls not on the physics, but on us. But I would not have you think that I regard this as grounds for despair. It is grounds for vigilance, which is a different thing, harder, more sustained, less dramatic, but ultimately more important. Because the solar sail, this fragile, gossamer thing, thinner than a blood cell, pushed by nothing more than the gentle pressure of light, the solar sail represents something that I find, in my more hopeful moments, genuinely moving. It represents the possibility of using the subtlest force in nature, the most delicate interaction between light and matter, to accomplish something that brute force cannot: sustained, patient, fuel-less travel across the vast distances between the stars. It is, if you will permit me the analogy, the opposite of the bomb. The bomb converts a small amount of matter into an enormous amount of energy in an instant of violent destruction. The solar sail converts an enormous amount of light into a small amount of force over an enormous amount of time, patiently, gently, without destroying anything at all. Both are applications of physics. Both are consequences of the same fundamental understanding of the relationship between energy and momentum. But they stand on opposite sides of something. Call it a moral divide, if you like, though the word moral is perhaps too simple for what I mean. There is a concept in the Bhagavad Gita, the concept of nishkama karma, action without attachment to the fruits of action, duty performed for its own sake rather than for the reward it brings. I have thought about this concept a great deal, too much perhaps for a physicist, though I have never believed that physics and philosophy are as separate as the professional incentive structures of the academy would have us believe. And it seems to me that the solar sail embodies something of this idea, a technology that does not force, does not burn, does not consume, but simply receives what is freely given and moves with it. The sun gives its light impartially to all things in all directions, without intention or discrimination, and the sail receives it and is moved by it and asks for nothing more. There is a simplicity in this that I find beautiful, and a humility that I find instructive, particularly for someone, for anyone, who has been involved, as I have been, with technologies that are neither simple nor humble. I have been wrong about many things. I have been wrong about people, about politics, about the possibility of controlling the forces that science unleashes. I was wrong to believe that the bomb would make war impossible. I was wrong to believe that reason, clearly presented, would prevail over fear and ambition. But I do not think I am wrong about this, that there is in the physics of radiation pressure a quiet lesson about the nature of force, a lesson that is worth hearing even if, perhaps especially if, one has spent a lifetime immersed in the louder and more terrible manifestations of physical law. The lesson is that the gentlest forces, patiently applied, can accomplish what the most violent forces cannot. That a photon, massless, traveling at the speed of light, carrying a momentum of Planck's constant divided by its wavelength, can, if given enough time and enough space, move a spacecraft to the stars. That patience is not weakness. That gentleness is not impotence. That the universe provides, in its own indifferent way, the means for traversal as well as the means for destruction, and that which of these we pursue is a choice that defines us. There are children playing in the streets who could solve some of my top problems in physics, because they have modes of sensory perception that I lost long ago. And I think sometimes that those children, who know what it feels like to stand in sunlight, who know the warmth of it on their faces, who do not yet think of photons as carriers of momentum or electromagnetic radiation as a solution to the rocket equation, I think those children might understand, more readily than I do, the simple wonder of being pushed by light. Before the equations, before the cross-sections and the pressure calculations and the area-to-mass ratios, before all the apparatus of theoretical physics that we bring to bear on these questions, before all of that, there is just the light and the push and the astonishing fact that the universe is constructed in such a way that the one can produce the other. Arthur Stanley Eddington, who confirmed Einstein's general relativity during the solar eclipse of 1919, who did more than perhaps anyone to make Einstein's work known to the English-speaking world, and who had his own gift for marrying scientific precision to literary grace. Eddington wrote that the stuff of the world is mind stuff, that the physical world is, in some deep sense, a construct of consciousness. I do not go quite that far, but I will say that the fact of radiation pressure, the fact that light, this most ethereal of physical phenomena, this thing that we associate with knowledge and perception and the inward life of the mind, that light carries momentum, exerts force, can push matter through the void. This fact suggests a universe in which the boundary between the material and the immaterial is not where common sense would place it. The light is not merely a signal. It is not merely information. It is a physical thing with physical consequences. And those consequences include the possibility, still unrealized, still distant, but physically grounded and no longer merely fanciful, of sailing to the stars on nothing more than starlight. The Greeks told the story of Icarus, who flew too close to the sun on wings of wax and feathers and fell. The story is usually read as a cautionary tale about hubris, about the danger of overreaching, of aspiring to heights that are not meant for mortals. And perhaps it is. But there is another reading, one that I prefer, though I recognize that my preference may be colored by my own history and my own particular need to find redemption in the wreckage of ambition. The other reading is this: Icarus flew. Before he fell, he flew. He left the ground. He felt the wind. He saw the sea from above. He approached the sun. And the fact that the flight ended in disaster does not negate the flight. It does not prove that flight is impossible. It proves only that the means must be right, that wax is the wrong material, that proximity to the sun requires not wax, but something that can withstand the heat, something that can use the sun's energy rather than be destroyed by it. And a soulless sail, this thin reflective membrane that does not melt in the sunlight but is propelled by it, is in a sense the answer to Icarus. Not wings of wax, but wings of light. Not a flight that ends in falling, but a voyage that accelerates patiently, year after year, carried by the gentlest force in the universe toward the most distant destinations imaginable. I do not know whether we will reach the stars. The distances are very great. Alpha Centauri is 4.37 light-years away, which is roughly 40 trillion kilometers, a distance that even at 20% of the speed of light would take more than 20 years to cross. and at the velocities achievable by current solar sail technology, would take tens of thousands of years. I do not know whether the engineering will be solved, whether the lasers will be built, whether the material science will produce sails thin enough and strong enough and reflective enough. I do not know whether the species that build such things will still exist when they arrive. These are questions I cannot answer, but I know this. The physics is real. The force is real. Light pushes. Maxwell proved it with equations. Lebedev proved it with experiments. Icaros proved it in the vacuum between Earth and Venus. And the fact that it is real, that the universe is constructed in such a way that the most insubstantial thing we experience, the thing that has no mass, the thing that is synonymous in every human culture with knowledge and truth and beauty, that this thing can move matter, can propel ships, can carry us, if we are patient and wise and brave enough, to the stars. This fact is, I think, among the most beautiful things that physics has revealed. Science is not everything, but science is very beautiful. And the light, which has been traveling from the sun to this earth for 8 minutes and 19 seconds, arriving with its gentle, persistent, infinitesimal push, the light is very patient, and the stars, for those who know how to sail, are not as far as they seem.